In clinical cardiology, Doppler ultrasonography is the application of the Doppler effect, a shift in the frequency of a wave relative to an observer moving compared to the source. In the heart, the moving objects are red blood cells, erythrocytes. Understanding how this translates from a pitch change to a color map or a spectral waveform requires looking at the interplay of fluid dynamics and wave physics. When an ultrasound transducer emits a pulse of frequency Ft, that is the transmitted frequency, the beam hits moving red blood cells. The cells reflects the sound back to the transducer at a shifted frequency, that is the reflected frequency Fr. The difference between these two is the Doppler shift, delta F. The velocity of blood flow V is calculated using the formula delta F is equal to 2 into Ft into V into cos theta whole divided by C, where C is the speed of sound in human tissue, constant at approximately 1540 meter per second. Theta, the angle of insonation, the angle between the ultrasound beam and the direction of blood flow. In Doppler echocardiography, the angle is quite important. Parallel flow, that is flow parallel to the beam. Theta is equal to 0, cos 0 is equal to 1. This provides the most accurate velocity measurement. Perpendicular flow, theta is equal to 90 degrees, cos 90 is equal to 0. The machine detects zero shift even if blood is moving at high velocity. This is why sonographers always try to get in line with the flow, like using apical 5-chamber view for aortic flow. If the angle exceeds 20 degrees, the velocity error becomes quite significant. This is a common pitfall when assessing stenotic valves. The heart handles a massive range of velocities from slow venous return to high velocity jets in mitral regurgitation. To measure these, we use two distinct modes. Pulsed wave Doppler. The transducer sends a pulse and waits for it to return from a specific depth, that is a sample volume. It has good spatial resolution. It tells you exactly where the flow is occurring. But the weakness is, it is limited by the Nyquist limit. If blood moves too fast, the machine cannot sample quickly enough, leading to aliasing, where the peak of the waveform appears on the opposite side of the baseline. Continuous wave Doppler. One crystal constantly transmits while another constantly receives. It can measure extremely high velocities like those found in aortic stenosis without aliasing. But there is a range ambiguity. It measures all velocities along the entire length of the beam, so it cannot tell you exactly where the highest velocity is occurring. Color Doppler is essentially an automated form of pulsed wave Doppler applied over a large area. We follow the BART convention, that is mnemonic, blue away, red towards, for coding the color of the flow. The machine assigns a color based on the mean velocity of the blood in each pixel. If the flow becomes highly turbulent, that is high variance, the colors mix into green or yellow, indicating a mosaic pattern often seen in regurgitant jets. The primary reason we care about Doppler velocity in cardiology is to calculate pressure gradients. We use the simplified Bernoulli equation delta P is equal to 4V squared. If you measure a peak velocity of 4 meter per second across a stenotic aortic valve, the pressure gradient is 4 into 4 squared, that is 64 millimeters of mercury. This conversion is the backbone of non-invasive hemodynamic assessment.